Hi, I'm creating this video for our informal image analysis class about how you go from an object to an image of it and how you can simulate that process. So part of this will be a bit of a recap of things we talked about at our Zoom meeting. So what do we see when we look through a microscope? As we discussed in class, a light-emitting molecule like this green fluorescent protein here is certainly not identical to its cartoon, but even if it were, this 2.5 nanometer wide object is not what we'd see when we look through even an ideal, platonic ideal of a microscope. So we don't see, a little bright 2.5 nanometer wide spot, but rather what we see is this, something that's much wider, noisy, and pixelated. So fundamentally, various physical aspects of light control this mapping between the object and its image. We're going to briefly examine this, but also do something practical, which is see how to simulate images. And as we discussed, this is extremely useful. It allows us to assess, for example, how accurate our image analysis algorithms are by testing them on simulated images. And we'll see examples of this as we go on in the course. As we noted in the exercises for this week, you'll either write for yourselves or write for yourselves a program that makes simulated images of point sources, or build on one that I wrote called modelimage.m. And I'll point out some aspects of this MATLAB function in this video while quickly recapping some of the things about image formation that we talked about in our previous Zoom session. So the perhaps most important thing about light is that it has a wavelength, and our green fluorescent protein, for example, here is emitting light with a range of wavelengths, all mostly centered around 509 nanometers. So visible light has a wavelength of a few hundred nanometers, and what that means is that even a point source doesn't look like a point, but rather a blur that's a couple hundred nanometers in size. In other words, looking at where the photons from this molecule come from, they come from a whole range of positions governed by this distribution that we see here. So this also is not what we would see under a microscope, but it's a little closer to that. Not a 2.5 nanometer wide spot, but rather this couple hundred nanometer wide blur. Now, this has a name. This is the point spread function. So another way of phrasing that is that the point spread function is the intensity distribution that a point source of light has in a given imaging system. Now, you can measure that, and in fact, this is often a very useful thing to do, by imaging a very small object, something that's much smaller than the wavelength of light, like a nanoparticle or a molecule or something like that. But also, especially for contexts in which you don't have much other aberration, like thin samples or stuff on a cover slide or things like that, the theoretical expressions for the point spread function are quite good, at least in the focal plane that you're imaging in. And that theoretical expression for most of the contexts that we care about is an area function. So what this looks like, so mathematically, it's a Bessel function of the position divided by the position squared, where the position is this kind of dimensionless measure of distance. So this v here is 2 pi over the wavelength of light times the numerical aperture of your system, which if you're using a conventional microscope lens, you can just read it off of the microscope objective lens, times the radial coordinate, how many microns in the focal plane you are. So this function, what it looks like, indicated as a surface plot, is here. We have this blurry, couple hundred nanometer wide, I shouldn't say blurry, sorry. We have this sort of spread out couple hundred nanometer wide spot. If you look carefully, it doesn't just decay monotonically to 0, but there's actually like little wiggles and oscillations, which you can actually see often in the actual images of a crisp object in a microscope. So here's our theoretical expression for the point spread function. So the first step then in simulating an image of a point source is, instead of your point source, using the point spread function. And this is done in my model image function by calling another program I wrote that just evaluates that function that's on the previous slide and calculates this point spread function on a sort of high resolution grid where each element in it is like a 2 nanometer wide square. And you can look at these lines in the function to get a sense of that. But this also isn't, as I mentioned, what we see when we look through a microscope. There's pixels. So every camera has pixels, and these typically are around 5 to 15 microns in size in modern cameras. And at the magnifications that one typically uses, this corresponds in the focal plane to an image scale of around 100 nanometers per pixel. And of course, you should know what that is for your exact system. Now, each pixel then catches the intensity in that 100 nanometer by 100 nanometer box. So step 2 in our simulated image is performing that pixelation. And conceptually, this is very easy. You just take buckets of 100 nanometers in size and put all of the intensity from that high resolution point spread function to those buckets. In practice, it requires some keeping track of the indices that map between the high resolution and the pixelated image, and doing that quickly, which is good if you want to make lots of simulated images. Takes a little bit of thought, and you can read about that in the for creating the pixelated CCD image section, and a couple of lines after that in my function. So that's still not what we see, because there's also noise. And this noise is also very fundamental. There's two types of it. One is really set by the basic physics of light and is fundamentally unavoidable. And the other comes from the camera. So let's talk about the intrinsic noise first. So this point spread function that I mentioned isn't actually the intensity distribution of light. It's actually the probability distribution of finding a photon at a given position. So where the point spread function is large, the probability is large. Where it's small, it's small. But yeah, it's not in itself that number, but rather the number of photons, but the probability of getting a photon. Therefore, we don't use our pixelated point spread function as is, but rather at each pixel, we draw a random number from a Poisson distribution whose mean is proportional to the value of the point spread function at that point. So in other words, if we did this many, many times, on average, our number of photons would just trace out the point spread function. But for any given instance, it's a random number from a distribution whose mean equals what's given by this point spread function. Okay. You can ponder that for a moment. Right, so we draw a random number from a distribution to get how many photons we have. To turn that proportionality into an actual equation, we need to specify how many photons in total our emitter is emitting. Now, this is related to the overall signal-to-noise ratio of the image. You can read about that in the things I've suggested to read. But as you might expect, if you have lots of photons, you have a high signal-to-noise ratio, the value you get from that random Poisson draw is going to be very similar to its mean. If it's low, we're going to have a lot of variation around that. Anyway, so you can relate the number of photons to the signal-to-noise ratio. Great, so step 3 here, we incorporate our intrinsic Poisson noise, and that's done just in one line in this program by calling a function that gives you Poisson random variables, and then doing the appropriate scaling to turn that into a number of photons. Cool. Now, as I mentioned, there's another source of noise, and this one is due to the sort of engineering of cameras, but it's still in practice unavoidable. That there's always intensity at pixels, even if you have no light shining on your camera at all, due to things like thermal excitation and other sorts of processes. Now, the form of this is camera dependent, and it can actually be rather complicated. Typically, it's considered as like Gaussian distributed or Poisson distributed noise about some mean, and so you can add that on as an extra noise source. In my program, I kind of simplify a bit by just allowing for only Poisson noise. You could also just add on a constant background or things like that. But in any case, we include some background level of noise as such. So there we go. Those are the steps. And at the end of it, we have our simulated image of a point source of light, our spread out, pixelated, noisy thing. And now we can do whatever we want with it. For example, tackling the challenging questions of how to go backwards from this to asking, okay, we see this, where was the point source that created it? And how precisely can we know that? Which is important for things like figuring out the structures of various biological objects like protein assemblies and so on, or tracking bacteria and things like that. Now, there's an added bonus to this overall procedure, which is that we can use it on all kinds of images, not just point sources, because you can think of any object as being built up as a collection of points, so you can simulate any object or the image of any object. The procedure is essentially the same. Since we're not starting off with a point source, we don't start off at step one with just the point spread function, but rather we take our, quote unquote, true ultra high resolution image and convolve it with the point spread function to get our blurred image of step one. And I'll leave it as an exercise to you to think about why convolution is the right thing to do here. Then, as before, we pixelate and incorporate both the intrinsic and extrinsic noise. Great, and so that's our overview of simulating point images and how we go from the object to the image. And I hope you found it useful.